Alright guys, as you may have noticed, I like the history of what makes human civilization great, and many of those pillars are minerals transformed into metals, and today I bring you aluminum. It is lightweight, resistant for many applications. It doesn't rust like iron, and in addition, it can be molded, rolled, and recycled relatively easily. And here's the interesting part. Aluminum did not become important because it was an exotic material. In fact, the original problem was exactly the opposite. Aluminum was everywhere, but for a long time nobody had a cheap way to extract it from the minerals that contain it. And that completely changed its history. Because when we finally learned how to produce it on a large scale, a material appeared that could reduce the weight of automobiles, airplanes, trains, electrical cables, containers, and many other things. Is it responsible for modern automobiles being more fragile compared to older versions? And keep this in mind. The most common mistake is to think that aluminum simply replaced steel because it was stronger. It doesn't work that way. Steel is still stronger in many applications. The advantage of aluminum lies somewhere else. You can obtain a structure that is strong enough while using much less weight. And in an industry where every kilogram counts, that can represent a huge amount of money. An airplane is the perfect example. If you can reduce weight without sacrificing the necessary strength, you can carry more cargo, consume less fuel, or increase range. And to understand how we got there, we have to go back to a time when producing aluminum was almost a laboratory curiosity. For a long time, aluminum was known mainly through its compounds. And here's a part that sounds simple, but was a real headache for chemists. Aluminum almost never appears in nature as pure metal. It is combined with other elements. One of its main sources is bauxite, a mineral that contains aluminum compounds. But extracting the metal from it requires chemically transforming that mineral. Simply put, nature doesn't put things on a silver platter. In fact, gold is another very interesting metal, noted title for another video, but anyway, nature gives you the raw material. And you have to separate it. During the 19th century, the first important advances in obtaining metallic aluminum began to appear. In 1825, Danish chemist Hans Christian Ørsted managed to produce an impure form of aluminum. After that, other scientists continued improving the methods of obtaining it. But producing it was still complicated and expensive. And that caused something quite curious. For much of the 19th century, aluminum came to be considered a luxury material. Yes, luxury. Not because it was particularly beautiful, but because it was difficult to produce. And when something costs a huge amount to manufacture, its price goes up. But then a combination appeared that changed the rules of the game. Chemistry plus electricity. In 1886, two young scientists, Charles Martin Hall in the United States and Paul Héroult in France, independently developed, practically at the same time, a method for producing aluminum through electrolysis. The process was named the Hall-Héroult process. Yes, the harder it is to pronounce, the better. And this invention was the real turning point. The idea behind the process seems complicated, but let's make it simple. First, you need to obtain alumina, which is aluminum oxide. Modern industry obtains this alumina mainly from bauxite through the Bayer process. Then comes the important step. The alumina is dissolved in a bath of molten cryolite. And through a huge electric current, the aluminum is separated from the oxygen. The liquid aluminum collects at the bottom of the cell. Then it is extracted and turned into ingots or other forms for further processing. It sounds simple when we explain it like this. But here's the detail. It consumes a huge amount of electricity. Primary aluminum production depends directly on electrical energy, and today electricity represents approximately between 20% and 40% of the cost of producing primary aluminum, depending on the conditions. And that explains something extremely important about the economics of aluminum. It is not enough to have bauxite. You also need abundant and relatively cheap energy. Until the end of the century, the cheapest energy was provided by coal, which has been changing, but it still represents a large part of the electricity that is produced. So you can't say I don't give you interesting facts. That's why the aluminum industry began developing strongly in places where large amounts of electricity were available. And suddenly, that metal that had once been almost a luxury could be manufactured in industrial quantities. That's where its real expansion began, because now manufacturers could start experimenting with it. Cables, machine components, structures, containers, and, of course, airplanes. And this is where aluminum found one of its most famous applications: aviation. When the first engineers were trying to build aircraft, they faced a huge problem: weight. An airplane needs to generate lift to stay in the air. And the more weight you add, the harder it becomes to make it fly efficiently. That's why the first airplanes used materials such as wood, fabric, and steel in different parts. But the engines also needed to be lightweight. And that's where aluminum began to demonstrate what it could do. In 1903, the Wright brothers' airplane used an aluminum crankcase in its engine. And this is important because the Smithsonian itself points out that this was the first time this lightweight material was used in the construction of an airplane. The Wright Flyer had an engine producing only 12 horsepower. Today, that seems like very little. But that engine had to be light enough so that the entire airplane could fly. And that was the advantage. They didn't need absolutely everything to be made of aluminum. They needed to place it precisely where reducing weight would provide the greatest benefit. Over the years, engineers began developing much more useful aluminum alloys. And here another important word appears: alloy. An alloy is a mixture of a metal with other elements to modify its properties. For example, adding copper, magnesium, silicon, or zinc can change the strength, hardness, weight, or behavior of aluminum. And this was fundamental for aviation, because the goal was never simply to build an aluminum airplane. The goal was to achieve the best possible combination of weight, strength, manufacturing, and cost. And that search was going to transform the industry. During the first decades of the 20th century, the use of aluminum began to grow rapidly. Aviation was one of the major drivers. It is worth mentioning that many of its advances during this decade were sponsored by the great global conflicts. But it wasn't the only one. Aluminum also began entering power lines, railways, automobiles, construction, and consumer products. Why? Because each industry found a different advantage. In electricity, for example, aluminum has a very interesting characteristic. It conducts electricity and weighs considerably less than copper. That makes it especially useful for certain power lines where the weight of the conductors matters. In transportation, the story is even clearer. Less weight means you need less energy to move a given mass. And here is a rule that repeats itself again and again. If you can reduce weight without losing the function you need, you've just created an economic advantage. That's why aluminum began appearing in engines, bodywork, structures, railway components, and later in countless products. But there was another characteristic that made it even more attractive. Aluminum quickly forms a very thin oxide layer on its surface. And although it may seem like a disadvantage that the metal oxidizes, this layer is precisely what helps protect it from much more aggressive further corrosion. Simply put, aluminum creates a kind of microscopic shield over its own surface. And that means it can last a long time in applications where other materials would require additional protection. But there was still another revolution to come. Because if aluminum was already lightweight, strong, and relatively easy to work with, they had to discover how to turn those properties into mass-produced products. And when industrial production began to grow, aluminum stopped being simply an interesting material. It became one of the pillars of modern industry. And this is where the history of aluminum changes scale. Because discovering a material is one thing, and building an entire industry around it is something completely different. During the 20th century, aluminum production grew enormously because machines began appearing that could process it at speeds that had previously been impossible. It could be rolled into sheets, extruded into profiles, cast into parts, forged into components. And that allowed the same metal to end up in completely different products. An aluminum profile can become a window. A sheet can end up in the fuselage of an airplane. A cast part can become part of an engine. And an extremely thin sheet can end up wrapping food. But here's something even more interesting appears. Aluminum is not only useful because it is lightweight. It can also be recycled without losing its fundamental properties. And recycling aluminum requires much less energy than producing primary aluminum from alumina. That's why a can that we throw in the trash today does not necessarily represent the end of its life. It can become raw material again. And this began to change the economics of the material even further. Because now aluminum didn't only have value when it came out of a mine. It also had value after it had already been used. And here we're going back to aviation because this is probably where the whole subject is best understood. A modern airplane isn't simply made of lightweight metal. Engineers select different alloys depending on what each part needs. For example, some aluminum alloys used in aircraft structures contain elements such as copper, magnesium, manganese, or zinc.
Why?
To change their properties. One alloy may seek greater strength. Another may offer better corrosion resistance. Another may be easier to manufacture. It's like cooking. You don't use the same ingredients to prepare every dish. And something similar happens in an airplane. Every kilogram has to justify its existence. Because that kilogram has to be lifted by the wings for thousands of hours of flight. And here an extremely important economic relationship appears. If a lighter structure allows you to carry the same load using less fuel, that difference can be repeated for years of operation. That's why aluminum came to dominate a large part of aircraft structures for decades. Although, keep in mind, that doesn't mean it's alone anymore. Today, modern airplanes combine aluminum with titanium, steel, and composite materials. And precisely that competition leads us to an interesting question. If there are materials that are even lighter and stronger, why do we still use so much aluminum? The answer lies in something we often forget. Manufacturing also costs money. You can have an incredible material on paper, but if it costs a fortune to produce, requires special tools, and is difficult to repair, the industry may think twice. Aluminum has a combination that is very difficult to match. It is relatively lightweight. It has good strength in many alloys. It can be machined. It can be welded using appropriate techniques. It can be extruded. It can be rolled. And there is a gigantic industrial infrastructure designed to work with it. That last part is worth a lot. Because when an industry has spent decades building machinery, tools, and processes around a material, changing it isn't simply saying, let's use another one. You would have to change suppliers, machines, training, processes, and even the way products are designed. And that's why aluminum appears in places where you may not even notice it. In buildings, in trains, in engines, in heat exchangers, in cables, in containers, in vehicles, and yes, also in the products we use every day. In fact, one of its most successful applications is practically right in front of us. Containers. An aluminum can be lightweight, strong, easy to transport, and also recyclable. And that combination made aluminum an extremely important material for the beverage and food industry. But there's another sector where aluminum became especially interesting: automobiles. And here the reason is once again weight. For decades, vehicles used huge amounts of steel because it was strong, relatively inexpensive, and there was an industry perfectly prepared to produce it. But as demands for efficiency and fuel consumption began increasing, reducing mass once again became a priority. And that's when aluminum began gaining ground. Hoods,
Doors.
wheels, engine blocks, suspension components, structures. Even entire vehicles can use large amounts of aluminum. But here an important disadvantage appears. Aluminum normally costs more per kilogram than steel. In addition, you cannot always replace a steel part with an aluminum one simply by making it identical. You have to redesign it. Thicknesses change. Connections change. Manufacturing processes change. And even the way certain parts are repaired changes. So the real savings are not always in the price of the material. They are in what you achieve thanks to that material. If you reduce weight and the vehicle consumes less energy throughout its entire lifetime, that's where the economic benefit begins to appear. And this explains why aluminum did not completely replace steel. The two materials ended up competing, but they also learned to work together. And if you want to understand another story where a material completely transformed an industry, in another video we talk about silicon and how a simple raw material ended up becoming the foundation of chips. Now look at something even more important. Aluminum doesn't just move goods. It also drives an enormous industrial chain. To produce 1 ton of primary aluminum, you have to go through mining, refining, transportation, electricity generation, smelting, processing, and manufacturing. First comes bauxite. Then the Bayer process transforms that raw material to obtain alumina. Then comes the Hall-Héroult process, where electricity makes it possible to obtain metallic aluminum. After that, the aluminum can be turned into plates, ingots, coils, profiles, or parts. And finally, it ends up in an airplane, an automobile, a can, a window, or a power line. In other words, when you buy an aluminum product, you're buying the result of a gigantic economic chain. And here is one of the most interesting details. Primary production depends heavily on electricity. That means the price and availability of energy can change the competitiveness of an aluminum plant. A region with abundant and relatively cheap electricity can have an enormous advantage, while another region may have the raw material, but producing the metal there may be too expensive. And there's still another variable coming in strongly: recycling. Because used aluminum already contains a huge portion of the industrial energy that was originally required to produce it. That's why recovering that metal can be economically much more attractive than starting over again from bauxite. And that's where aluminum begins to stop being merely a lightweight material. It becomes something much bigger. A piece of the global economy where energy, mining, transportation, manufacturing, and recycling ultimately connect within the same chain.